Unit 3, Homework 1. As before, my questions are probably in a different order than yours, and any numeric questions probably have different numbers. So my question 1, when would an EDTA back titration be necessary? Well, EDTA back titration is necessary if the target analyte precipitates without the EDTA, if it reacts too slowly with EDTA, or if the target analyte blocks the indicator. So that's when we need to use an EDTA back titration. Question 2, a 50 milliliter solution that contains both nickel and zinc was treated with 25 milliliters of EDTA to bind all the metal. The excess unreacted EDTA required 12.4, so we're told excess EDTA, which means we're working one of these problems where we have a total EDTA is going to be equal to the excess plus reacted. So the excess is what we're going to calculate first because that's what I have. Or that's what's told to me very clearly. The excess unreacted EDTA required 12.4 milliliters of magnesium with this concentration. So we know that EDTA reacts 1 to 1, so 1 mole of magnesium reacts with 1 mole of EDTA. That means my excess EDTA, 0.0124 times 1.896 times 10 to the negative 2. I have 2.35104 times 10 to the negative 4, and that is moles of EDTA in excess. But I also have that total. So before I read the rest of the problem, I'm going to calculate my total. So the total EDTA is 25 milliliters, so 0.0250 liters of 4.34 times 10 to the negative 2 moles per liter. Just multiply those together. And my total is 1.085 times 10 to the negative 3 moles of EDTA. And I don't know how much is reacted. I can find out how much is reacted with a simple subtraction problem. So I'm going to calculate that even before I read the rest of my problem. So I know that my reacted EDTA is 8.49896, and I'm not rounding on purpose here, times 10 to the negative 4, and that's moles of EDTA that reacted. So now I can read the rest of the problem. An excess of the reagent 2,3-dimercapto-1-propanol was then added to displace the EDTA from zinc. Another 29.2 milliliters of magnesium, and that's at the concentration that was given before, 8960 times 10 to the negative 2, were required for reaction of the liberated EDTA. Now, what did that displace? So the magnesium is calculating how much zinc was let go. So this magnesium that reacts 1 to 1, so 1 mole of magnesium reacts with 1 mole of EDTA, and 1 mole of EDTA is liberated by 1 mole of zinc. So I'm actually calculating how much zinc reacted, but I need to convert this into liters, 292 liters. So I get that there were 5.53632 times 10 to the negative 4 moles of zinc. Now the question asks, what is the molarity of nickel in the original solution? Well, I have the moles of zinc. I have how many moles of EDTA total were reacted. So again, we have a total reacted is going to be equal to moles that reacted with zinc plus moles that reacted with nickel. Now the total reacted EDTA is going to be 8.49896 times 10 to the negative 4. And again, that's moles of EDTA that reacted with the original solution. So the moles of EDTA that reacted with zinc, see, I could stop this right here, all the same. Moles of EDTA reacted with zinc, 5.53632 times 10 to the negative 4, and I can get the moles of nickel in the original solution. And it's just a subtraction problem. So I get that there were 2.96264 times 10 to the negative 4 moles of nickel in my original solution. The question asked for the molarity. So I need to divide these moles by the liters of the original solution. So 0.050 liters. And I get 5.9, I'm going to call that 93. And that's times 10 to the negative 3 molar. My question 3 has uncertainties as well, so we're looping the first unit back into this one. So we have a potassium ion in a 250 plus or minus 0.1 milliliter water sample was precipitated with sodium tetraphenyl borate with this reaction. Precipitate was filtered, washed, dissolved in an organic solvent. So treatment of the organic solvent with an excess of mercury 2 EDTA then provided us with this reaction. It's already balanced. That's nice. The liberated EDTA was titrated with 28.73 plus or minus 0.03 milliliters of 0.0437 plus or minus 0.1231 capital M molar of zinc. Find the concentration and the uncertainty of the potassium in the original sample. This one's going to require quite a bit of stoichiometry. So we're going to start with the volume of our zinc. So 0.02873 liters of zinc. And I'm going to multiply that by its concentration, 0.0437 moles of zinc per liter of zinc. And I know that 1 mole of zinc will react with 1 mole of EDTA. Now I need to use the stoichiometry found in my equation. So 4 moles of EDTA, that's what the HY3 minus is. So 4 moles of EDTA react with 1 mole of the tetraphenyl borate, TPB for short. And 1 mole of tetraphenyl borate reacts with 1 mole of potassium. So originally I must have had 3.138725 times 10 to the negative 4 moles of potassium. The question wanted the concentration, so then I need to divide that by 0.2500 liters. And I get a concentration then of 1.2, looking for significant figures. Looks like I'm going to be kept to 3 significant figures. So 1.26 times 10 to the negative 3 capital M molar for my potassium. That's my concentration. Now what's the uncertainty? So I had uncertainties in this value, this value, this value. When we're multiplying, because what we're doing is multiplying and dividing, remember we're finding that E%, and that E% is going to be the square root of 100 times the uncertainty, and I'm actually going to start with my 0.028 volume. So the uncertainty of that is 0.03, and divide that by my 28.73. I need to keep these units the same. Square that value. Then 100 times, I'm looking at the concentration of the zinc now. 3 zeros into 1 divided by 0.0437. Square that. And then I have the water sample volume, 0.1 divided by 250, and square that. So the E% of this concentration, I'll stop here for a second so you can check my work as well. Underneath the radical, I have 0.064868 and such. So I need to take the square root of that value, if I did that right. So the E% is then 0.25469. That's what I get. So the uncertainty then, we could report this as 1.26 times 10 to the negative third molar plus or minus 0.3%. Or you could report this as 1.26 times 10 to the negative 3 plus or minus 0. Let's see if I'm 10 to the negative. Let's make this part the same. So then it would be plus or minus 0.123 times 10 to the negative third molar. For number 4, this is actually a 2-layered problem. So first we have a 25 milliliter sample that contains both iron and copper. Now, the collection of these metals required 0.01606 liters of a 0.05083 mole per liter EDTA solution. Now, because EDTA reacts 1-to-1, so 1 mole of EDTA reacts with 1 mole of any metal, I'm just going to use the word metal here, then the moles of EDTA that were used are equal to the total moles of metal in our unknown sample. So this ends up being 8.163, or 8, seems I can't read my own writing, times 10 to the negative 4, and that's total moles of metal. So then we have a 50 milliliter sample. So now we have 50 milliliters of our unknown, and we're going to treat it with some ammonium fluoride, and we're going to protect that iron. So then the copper is reduced and masked. On addition of 25 milliliters of our EDTA solution, then the iron 3 is liberated, and we form that EDTA complex. So 1 mole of EDTA reacts with 1 mole of iron now in this 50 milliliter sample. So the moles of EDTA used for the metal, for the iron itself, can be found by taking this total EDTA, because this one's total, 0.025 times 0.05083. And that is 1.27075 times 10 to the negative 3. That's our total EDTA in the second titration. That's going to be equal to, the very next sentence gives us the excess. So the excess EDTA is then going to be, so our total is going to be equal to excess plus reacted with the iron. That's the point, is we want to find out how much iron was there. The excess can be found by taking 0.01977 liters and multiplying it by 0.01883 moles per liter of lead, because 1 mole of lead will react with 1 mole of EDTA. So 0.01977 times 0.01883. The excess is then 3.723 times 10 to the negative 4. So with a simple subtraction problem, I can find out how many moles of EDTA were required to react with iron. And with a simple subtraction problem, I get the moles of EDTA that reacted with the iron. This is in the second titration now, is 8.98. I'm going to call that 5 times 10 to the negative 4. And again, that is moles of EDTA that reacted with the iron. So how much copper was in the unknown? Now we have to work a little bit of algebra. So we have 8.985 times 10 to the negative 4 moles of iron in a 50, there it is, 50 milliliter sample. My original unknown was a 25 milliliter sample. So we would expect to find 4.492 times 10 to the negative 4 moles of iron in my original sample. So I can replace up here 4.492 times 10 to the negative 4 moles, and I can find out how many moles of copper there were, again, with a simple simple subtraction problem. And I get that there were 3.676 times 10 to the negative 4 moles of copper in the original sample. But the question asks for the molarity, so then I need to divide that value by 0.025, which was the original sample volume, and I get a copper concentration of copper is then 0.01470 capital M molar.